Hi guys. Hey everyone. So a little bit of a impromptu video. So I'm gonna have this uploaded for everyone, whether or not you are in person class or a virtual class. Um, Heck, I might even upload it to YouTube. So that way, if any students, future students who take the screed, or anyone really out there takes the screed, I guess we can use this as a kind of template, I guess. I'm not sure what really the plan is, but um, ultimately, when it comes to this, the idea with this was that I know that at least for it's the time I'm recording this, which is July 25th, 2023, uh, I believe there's something called a final coming up for um, COT 3100C. So I recognize that some of it can be a little bit intimidating, and a lot of the material can be challenging. So what I wanted, my goal was essentially we're going to kind of start from the beginning, work our way back, back all the way to where we are now, and the hope is that along the way we can do some questions that might challenge us, and we'll kind of see what happens. And so why not we kick it off with the first thing that we learned. So I'm going to kind of title this a little bit differently. So we're going to call this the Ultimate Study Guide. And the idea is that with this, we're going to basically kind of have this be a one-stop shop to be a crash course. So first note, for the first note, um, this is just a crash course. Of course, please try not to accept this as like the be all end all. There is there's so much more than just the concepts I'm covering here. My goal is just to give a basic idea of what introduction to discrete structures really entails. And obviously, every whether you're in Professor Mead's class, which is COT 3100C, or you're in Professor Gerber's class, Professor Guha's class, or even in another college. So this gets uploaded to YouTube. The idea is I wanted this to be kind of a general catch. So let's get started, shall we? So the first thing that we covered in this class is something called propositions. And this is so let's talk about propositions. So the joke is among this class, or I guess I guess it's a bad way of saying it, but the joke is that um, the first proposition you probably heard was somewhere along the lines of "Will you marry me?" And unfortunately, that's technically not a proposition. They kind of lied to you. Oops, sorry. So we're already starting on the wrong foot. But the idea is this: so propositions at its core, at its core, is simply a declarative statement, if I can ever spell, a declarative statement that has a truth value of some sort. Now, it's a lot of. It seems simple, but there might be a little bit of confusion. So first off, what do we mean by um, truth value? And so this introduces the idea of what is called Boolean algebra. So in regular mathematics, which is elementary school, middle school, high school, and even some classes before introduction to discrete math, you've worked with like regular algebra, how I would call it. So 1 plus 1, 2 plus 2, 2 times 2, all that jazz. Um, we work we are in this for the first few topics, we're working with what is called essentially Boolean algebra. And the idea with Boolean algebra is that it's, well, algebra, just with truth values. And it has different operations compared to regular math. Um, truth truth values refer to simply true or false. Those are the only two truth values that we have in or two truth values that we have when it comes to Boolean algebra. And so the question is, well, how does this even work? So let's show you an example of how we use this. So for examples of propositions, if a proposition is supposed to be a declarative statement that has a truth value of some sort, so the examples could be as follows. So we could say the following: the sky is blue. Uh, that's a that is a declarative statement that has some sort of truth value because it's either the case that the sky is blue or the sky is not blue. So that's an example of a proposition. We could say pigs can fly. That's another one. That's another common one that is a proposition. Um, we could say that 1 plus 1 is equal to 2 because 1 plus 1 is equal to 2 has a truth value in terms of whether or not it is a correct equation or not. We could say that 0 is equal to 1. And we can say also things such as um, probably some outlandish stuff, such as the universe is ending, which, depending on where you're from, or depending on where you're from, maybe sometimes it might feel like the universe is ending. But at least at the time I'm recording this, the universe hasn't ended. So fingers crossed that it keeps going at least for a few more days. So those are kind of like examples of what we call propositions. Basically, notice that for all of these propositions, notice that for all these propositions, they or for we're not gonna say propositions. Note that for all these statements, every every one of them has either a true or false value. We can definitively say that either the sky is blue or the sky is not blue. So that's what we mean when we say truth value. So what are examples both of statements that are not propositions? Um, we can say the most common statement that is not a proposition are questions. Questions such as what if what if I am not a human? Well, that doesn't have a truth value. There's a result for it. We don't say true or false as a response to this question. We can say that, and the other common one is when we have some sort of equation where it's using a variable, x is equal to 1. Technically speaking, it's kind of a proposition. This one's a little bit special. No, little bit of a special case. We'll come back to him in a bit in the future. So these are, but other questions such as, will you marry me? Obviously, that's the big one. Um, this is not a proposition because this isn't asking a true or false value. This is a yes or no. And so these are examples of statements that are not propositions because as all of the statement the bullet points above are statements that are not definitively can I spell definitive? God, how do I spell definitively? Time out. No. Oh no. There we go. Definitively, English is not my strong suit. I am so sorry. Definitively, true or false? And so, well, these are examples, there's basic examples of like what is a proposition and like what is not a proposition. And that's pretty much like the very core of discrete math because at its core, discrete math is all about logic. It's simply proving things because really it's simply, hey, I ask a question and give an answer, and that's great and all, but you have to tell me why something works or doesn't work. Unfortunately, the best analogy I can think of is like that annoying 5-year-old who always asks, "But why, mom?" Uh, the mom will always give a reason. It's like, "We can't do this, Timmy, because we don't have enough money." And then Timmy asks, "Why don't we have enough money?" And it just becomes a never-ending loophole. And so that's what essentially discrete math is. It's just that 5-year-old kid always asking a lot of questions. So now we know how to say simple propositions. It's basically saying statements that have some sort of truth value. But we are not limited to simple propositions, especially in the real world. We say a lot more complex sentences, especially in English. So the question, the question is simple. Like, how do we form more complex statements or complex propositions? So how do we do that? The the key answer to this is with this idea of connectives. Connectives are essentially symbols that help combine the proposition. So if you want to imagine it, in the English language, let's say I have one sentence that says the sky is blue, and then the other sentence is, for example, I ate pizza today. So the sky is blue, I ate pizza, and I want to like essentially combine those two propositions into a single like super proposition. And the question is, how do I do that? The answer is with connectives. The answer the answer comes with connectives, and connectives are pretty much symbols that help join propositions together. In English, in English, they are the words. So, or I don't want to say specifically the words, but they are what does the English teacher call them? They're essentially like I'll say this. They're essentially bridges that help help combine multiple statements together. Again, please don't judge me on my really bad English. Apologies. Yeah, not the best. Whoops. Guess that's why I wasn't really an English major. Um, but the idea is that connectives help join multiple statements together in English. So in the discrete world, they're going to help us join multiple propositions together. So what are these connectives? And there's quite a few of them, but I'm going to give us about 6 of them. We'll give about 6 of them. But for the purposes of how I'm going to essentially discuss this, we're going to really focus on 4 of them. So they are as follows. So the first one we have is called the wedge symbol. So the wedge symbol is really this like caret looking guy or exponent symbol. This this sim this symbol is the and symbol, and word in English. So if we want to say like and like two events have to happen simultaneously, typically we say and to denote that both conditions must be satisfied. To do that, we use what is called the wedge. We also have the V symbol. The V symbol is this guy here, looks like a V. And in English, this symbol is the or word. So as either one event happens, or the other event happens, or both events happen. So those are the first two symbols. The next one we want to say is um, the negation symbol. Now, there's quite a few different ways that um, professors write the negation symbol. The way I know it best is the seven looking symbol, or as I like to call it, the door handle. Um, I've heard some people call it the backwards gun. Um, Not sure how appropriate it is, but I'll call it the door handle. So the negation symbol is this door handle looking symbol. And in English, this is the word not. And then finally, we have essentially what is called the implication symbol. The implication symbol, which is this light arrow looking guy. And this symbol is not just not just one word. This one's a little bit clunky or interesting, if however you want to see it. But this symbol it is the phrase if and then I'm gonna say insert something here, insert something here, if then insert more things here. So basically, if something happens, then something else has to happen. Kind of think of this as a contract of some sorts. And the idea is that each of these four symbols that I just listed are the foundations from which we can create any type of complex proposition. This is how we really turn English sentences kind of into complex or complex propositions in the discrete world with symbols, and then we can do the reverse, vice versa. It's kind of part of our curriculum that we kind of want you guys to make sure that you can do both of these things kind of seamlessly, because you can do it here, you can do it anywhere, and it really does help set the foundation. But obviously, I said that there were six symbols. There's only four of them on this paper. So question is, where are the other two? And so the other two are kind of are kind of interesting. So we also have the by implication symbol. And this one is the left and the right arrow. So together it would look something along the lines of like this, where you would have two, instead of one arrow, you would have two arrows coming out, one going to the right, one going to the left. It's denoted, hence the idea of by. And so this symbol is the phrase if and only if. If insert something, and only if insert something. Yeah, in English. So that's what the by implication symbol represents. And then the final one, the really funky one, is this symbol, this plus with a circle around him. We call him the exclusive or XOR is how we call it in the logical world. And his symbol is the plus symbol with a big circle around him. And this symbol is just the phrase exclusive or, meaning, and this one's a really funky one. I kind of like the way we say this is really either one event happens or the other, but not both. I don't really like this exclusive or, so we'll say this is also the phrase. Oh shoot, this is where it's going to be really complicated. So this phrase is also the word or. However, it's don't confuse this for the V symbol here because this one is a these the uses of our ors is a little bit different depending on this. And this V symbol, this this or means either one event or the other event has to happen. It could be and it can be the case that both both events occur. Here, either one event happens or the other, but you can't have both of them happening. So that's the main difference between the regular or and the exclusive or. What I would say is in terms of which ones are, I guess, the most important, I would say the first four are really the foundations of discrete math because it actually turns out, and we'll kind of show this a little bit later, but it turns out that the wedge, the V, the negation, and the implication are all the foundations of discrete math. The by implication and the XOR can actually be rewritten in terms of these four symbols, and we'll show that in the future. So now the question becomes, well, this is fantastic and all, but like, what's the whole point? Like, why do we do this? So obviously the question now naturally just becomes like, so what's the point? So the point is this. The idea is that all these symbols that we listed help us create complex propositions. So most likely, if you are watching this, if you watch are either reading this or watching the video, you are not an English major. You are not an English major at all. No offense to English majors. Like I have good friends that are English majors, so please don't come for my head. Um, but most likely, if you're reading this document or watching the video, you're not an English major. That means we want and oh, and furthermore we like to say stuff. We always like making things easy on ourselves. We don't like writing big big English statements. Again, unless you're an English major, because that's kind of what the job entails. But we don't like writing big English statements slash sentences. So the idea is that we want to find the quickest way to get the point across without having to write a giant sentence. And that's what connectives and propositions really helps out with. So let's show an example of how to write a basic a basic I'm going to put basic in quotations, but a basic complex proposition. So let's say I have the following sentence. Let's say the following sentence is I passed intro to discrete structures and I am a college student. Now, the point of this is the point of writing this is as follows. That's a very long sentence, long in quotation marks. And I don't want to keep writing this over and over and over again. So there has to be a faster way to write this rather than saying this over and over again. Luckily, there is. The idea is that we're going to use essentially propositions. So what we're going to say is we're going to use a common we're going to use the connectives and propositions to help it. So the idea is that let's say that P represents the statement I passed intro to discrete structures. And let's say that Q represents the statement I am a college student. So now, wherever I see these phrases, I just essentially plug in P and Q. So now, I have my sentence. My sentence just becomes essentially P and Q, where we have this as our essentially key to transferring I-pass intro to discrete structures, where that turns into P, and then Q turns into I am a college student. So instantly, this is a lot better, but I'm even lazier. So now what I'm going to do is I'm going to look at this word here. It says and. I know what and is in the connective world. In the connective world, and is the wedge symbol. So now I'm going to take the word and man, this is definitely a little bit uh interesting, but I'm going to take the word and replace it with the wedge symbol. So now the proposition turns into P wedge Q. That's a lot easier to write than saying this. So now instead of having to write the sentence, I passed introduction to discrete structures and I'm a college student, I simply just write P wedge Q, which is miles and eons better than what we had to write. And unfortunately, I did run out of time because I try to keep these into like smaller tidbits. But this is like the core understanding of essentially what propositions and connectors are about. But the question is, remember, we're now in Boolean algebra. There might be a little bit more that we can do with these symbols rather than just simply turning English sentences into symbols. And I'll go over that next time when I upload a video. When I upload the next video, which is going to cover what are called truth tables. We're going to cover uh, order of precedence, like how a kind of like a PEMDAS, if you want to think about it. And then the final thing we're going to kind of talk, and then the next, we're also going to talk about predicates in that next video. I hope this video, whoever watches it, helps out a little bit explaining the concept of propositions. And until next time, I will see you guys on the next video. Until next time, guys.